Welcome to episode 7 of Crashcourse Cryptography. My name is Julian, and in this entire Crash Course series, we go all the way from basic introductions of what cryptography is, down to the deepest holes of cryptography that's used in cryptocurrencies and in blockchains all around the world. And today, we are finally starting with asymmetric cryptography. Yeah! And we are starting with, at the moment, still the most popular asymmetric cryptography used out there, especially on the internet. And that is RSA, developed by the acronym of the three founders or the three developers, Rivest, Shamii, and Adelman. And this is going to be very interesting because on the one hand, this is not something that's being used in cryptocurrencies or in blockchains, and we're going to be talking about why. But it's still uber essential to understand how RSA works, because if you're using a browser, if you're using email, if you're using credit cards, literally anything that's out there at the moment still kind of is based on RSA. And the fundamentals and the concepts are very essential to understand. So let's go into the writing pad and let's kind of discuss a couple of things. So we are part 7 and we're going to be discussing RSA. Now, remember, quick summary, when we talk about asymmetric cryptography, we want to be able to do a few things. The first thing we want to do is we want to encrypt and then obviously decrypt. And we want to be able to sign. Now, the signing is something that we're going to be discussing in one of the later episodes, so we're not going to be discussing it today, but I can tell you already, if you want to do some extra credit work, then all you have to do is you just kind of inverse the encryption and decryption process. So you just basically decrypt with your key and it would work straight away, and then the other party can basically encrypt or prove that you actually signed it. So it's very, very straightforward. The other thing that you should remember on all these asymmetric cryptography systems that we're going to be discussing, so RSA today, next episode is Diffie-Hellman, and then we're going to dive deep into elliptic curve cryptography, are the down and the upsides. The downsides are that they're very mathematically intensive, they're very computing intensive. But then obviously the upside is that I can have this public key that I can share with everyone. And that is something that's very, very interesting to understand in this entire concept. Many times, especially on the internet, and RSA does this, these asymmetric cryptography algorithms work together with symmetric ones. So in this case, RSA works together with AES, something we discussed in the later episodes. In cryptocurrencies and in blockchain, this is not the case. And it wouldn't have to be the case in RSA. It's just you have a bit more computing to do, and there's just a lot more to do there. So let's kind of get some history here. This is just really, really brief history as some background. I think it's always kind of interesting to understand where are we in this entire concept. Actually, RSA was not the very first asymmetric cryptography that kind of was defined. Actually, the very first one was Diffie-Hellman, and that happened in 1976. So it was quite some time ago if you think about it, over 40 years. So they kind of knew this. But then Rivest, Shamii, and Adelman developed RSA in 1977, so a year later, and they based it on the ideas that Diffie-Hellman had. And you will see, and this is going to be something that's important, none of these concepts that we're going to be discussing today are new concepts. They actually just stack together. Mathematicians understood these things for a very long time, and we're going to be referencing all these theorems and all the proofs for correctness. But this is very important to understand. They didn't do anything new. They just kind of had a new, better idea. And this is something that's quite interesting and to me always quite relevant, that it's not always about coming up with completely new things. Many times it's taking existing building blocks and putting them together, maybe in a bit of a different way. Now, RSA did have a big downside. RSA was patented until the 2000s. And obviously, it was quite hard to work with it. This is also something that, for example, Schnorr had until quite some time ago, also something we're going to be discussing a bit later. But this is always a bit of a challenge, right? If something is not open source, this is always a bit of a trick here. And so this is kind of a bit of the history, but since then, especially together with AES, RSA has been mega widely used in the entire internet system. So this is something to really kind of understand and kind of always remember. Now also remember, we did this example in the second lesson where I gave you this public key 5 and then suddenly I knew a private key and I could encrypt and then decrypt the message. And so what I want to do today is I want to show you how I came up with these numbers and how this in principle kind of works. And you will see it's actually very, very fascinating to see all this. As a very quick reminder, so let's kind of get this. Remember, the encryption function and the decryption function is the same. It's just that the keys are different, right? So in this case, we have the ciphertext, and it's the plain text, to the power of an encryption key, and then the entire thing is mod n. In our case, if you remember, we had the encryption key that was 5, we had n was 14, and then we had the decryption key that was 11. And so we need to discuss where this came from. Now x is pretty much the same thing, y to e mod n as well. And so now it's going to be interesting to understand these concepts. RSA is actually quite straightforward. RSA has, and these are the steps, it has 5 steps. And these are always the same 5 steps. They're going to be discussed widely, and they're pretty straightforward. And what you start with is the very first step, is you need to come up with 2 prime numbers. Now, again, just if you don't know this in number theory, prime just means that a number is only able to be divided by itself and by 1, right? So 2, 3, 5, 7, these are all prime numbers. We're going to talk also about a name called coprime. Coprime means if I have 2 numbers, for example, 5 and 7, that they are prime to itself. Now this is going to be very relevant. Now obviously a prime number is always coprime to another number, unless you have a multiple of this number. So 7 and 14, even though 7 is a prime, it's not coprime because 7 and 14 are divisible. If you understand what I mean, there's no leftover, right? So this is very, very important. Now here, we need to choose, in step 1, we need to choose 2 primes, and they'll be called P and Q. Now this is very relevant in normal cases. So if we did something out there, P and Q would be 2 to the power of 512, right? A minimum. So 2 to the power of 512 each. So these are really, really, really lengthy numbers. And we are doing this because what's going to happen is we're going to multiply those into n. Because n, so remember, n is the modulus. N equals P times Q. And so this is important because if we do this, and P and Q are each 2 to the power of 512, so 512 bits, this one is at least 1024 bits. And we need this because otherwise we're going to be able to crack this. And we're going to be discussing a bit of cryptanalysis at the end, but so we need this kind of length. And you will see this is going to be the major downside that RSA has. These keys are insanely long. I can already tell you, for example, in elliptic curve cryptography, we're using 256 bits in length. And so if you think, oh, 256, 512 bits, that's not much difference, think about it. Always another number there, so 2 to the power of 257 is twice as long as 2 to the power of 256, right? Remember the power of adding another number as the exponent. This is always a bit tricky. So there's a humongous difference between 2 to the power of 256 and in this case 2 to the power of 1024. So never forget that, right? So this is very, very important to always remember here. Now the numbers that I used in this example is P equals 2 prime and Q equal 7. Now I could have used any other number, but I'm just kind of using these examples here. And so now what happens is I get n equals 14, and this is where this modulus comes from. Now I can tell you already, it's very, very important that P and Q stays private. So P and Q is not allowed to be shared, and they have to be that large so they cannot be guessed. Because if you know P and Q, and you will understand why, you're going to be able to crack a setup RSA system. So that's very, 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 very important. Now here comes the next step that we need to do. And we need to calculate Euler's fee. And we need to calculate that, and I'm going to explain this in a second, because Euler's fee plus 1 equals going at least one, but a full round around the circle. So it's basically, if you have a clock, then on the modulus you're choosing, in this case we're choosing modulus 14, we need to ask how many steps do I need to walk in this field and group. So if you kind of skipped this lesson from last time, you should go back to understand this. How many steps do I need to walk until I walk a full round? And I'm going to be explaining this, what this actually means and how this works in just a second, but I just kind of want to explain this to you. So what is Euler's fee? Euler's fee is actually the amount of numbers that are co-prime to n in this case. So the question is, what are the numbers that are co-prime to 14? So we could go through and we could say, okay, 1, 3, 4 is not, 5, 6 is not, because 2 is in 14 and in 6, 7 is not, 8 is not, 9, 10 is not, 11 is, 12 is not, and 13. So we have 1, 2, 3, 4, 5, 6. So in our case, Euler's fee is the number 6. Now, this is impossible to do because we need to count so many numbers. So think about how long n is. So it would take forever to count all these numbers. So there's actually a way to calculate this. And this is called Euler's theorem. You can look this up. We're not going to prove this right now. I'm going to actually skip a couple of proofs here. I'm going to tell you that they exist. And the reason I'm skipping them is because this is quite boring math, and you're just kind of proving and calculating this through. This has been done hundreds of years ago. Many times you learn this in school, so you can look this up. It's not the most exciting thing to do this. It's way more important, and sadly a lot of people, a lot of teachers, a lot of videos don't explain this to you, why it is relevant, right? So today you can do all this with a click of a button, and I don't need to calculate all this myself. I just need to understand, why am I doing this? So you can look, and this is called Euler's theorem. So I'm not going to explain this. I'm going to explain it, but I'm not going to prove it or calculate it through. Now what you can do is, there's actually a way easier way to calculate how many numbers are co-prime to a number if you can prime factor it. Because there's a very, very nice way. If I ask you, let's use a prime number. So let's use the number 7. How many numbers are prime to 7? So let's say 7 is p. Well, it's very easy. All the numbers until p minus 1. Because they are all co-prime. By definition, they have to be. So in this case, it's always p minus 1. In this case, it's 6. Now here's the interesting thing. I can factor the larger number into those primes if I know the factorization, and I can just multiply the number out of it. So in our case, Euler's fee is actually p minus 1 times q minus 1. And that is actually the formula under step 3, how to calculate Euler's fee. So that is why it's so important not to disguise 2 and 7, p and q. It's mathematically very, very difficult to calculate p and q if you only know n, because remember, n is public. This has to stay private, and the reason it has to stay private is so that no one can calculate phi. I will tell you why it's going to be essential not to be able to calculate phi in a second, so right now you just have to take it. So let's do this in this way, and so we have 2 minus 1 times 7 minus 1. So that's 1 times 6, it's 6, which is the same thing that we did by counting. Very straightforward. So that's step 3, count Euler's fee, calculate Euler's fee, and Euler's fee actually then plus 1 is going to be the number of steps it takes to make a full round. It can be 2, 3, 4 rounds, that depends. This is going to be a discussion we're going to have, but that's basically why we need this fee. Now, step 4 is, and I'm going to explain you why we need this, we're looking for a number that's smaller than phi and is co-prime to phi. And I'm going to tell you why we need this. So in case of 6, so let's not take the 1. So 2 is not co-prime. So 3 is not co-prime. 4 is not co-prime. 5 is co-prime. So this is going to be, and that's different to any other cryptography that's public. So that's different to Diffie-Hellman. That's different to elliptic curve. Here, we're choosing the public key, which is the encryption, first. It's very important. In elliptic curve cryptography, we choose the private key first. And actually, we shouldn't be choosing it. We should be randomly taking it. Here, the public key many times is a number that's very, very small, very, very easy because we're giving it to the public anyway. So there's very specific numbers that are being used here because this public key actually is not that relevant. The difficult part comes now in part 5. And so what you normally do is you have to test this, and you test this with what's called the basic Euclidean algorithm. Now, I'm not going to go into this. This is basically how you calculate greatest common denominators, GCDs. This is what school kids learn in school. You can look this up. There's a button to click on a computer that calculates greatest common denominators. I'm not going to go into detail how to do this. You can watch YouTube videos if you want to. But basically, you can take any kind of two numbers and ask what's the greatest common denominator. It takes a millisecond to calculate this. Because you just use the basic Euclidean algorithm. It's very important always to understand what's very easy to calculate and what's really difficult to calculate. Calculating this public key, if you know phi, is very, 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 very easy. And you can select. So in our case, because we chose such small numbers, I can only use, in our case, 5. Right? So I'm going to use 5. And the reason it has to be co-prime, that's important, is because I need to calculate the inverse. Remember, this is from the last episode. We discussed multiplicative inverses. And so what I need to calculate is 5 times, and this is going to be the decryption key, mod equals 1 mod phi. So in our case, phi is 6. So I need to ask, this is the encryption key, this is the decryption key. What's the inverse to get 1 mod phi, in this case 6. And so what you normally would use here is the so-called extended Euclidean algorithm. And you can calculate that. You can calculate it quite easily if you know the phi, the modulus in this case, and you have, and that's important obviously, a co-prime number, so you can actually calculate an inverse. Computers can do this, doesn't take too much time, so you just have to calculate those. So in this case, E, we choose you have very typical encryption keys out there, public keys, but now comes the private key, right? Remember, this is the private key. This one is public. This one goes public. Let's mark this, public. This one stays private. Very important. This one is public. This one is private. And this last one is private. So, if we're calculating this, and now we would have to use the extended Euclidean algorithm, we're not going to go into detail how to do this, we're just going to try it through, right? So if I do 5 times 1 mod 6, well, it's 5. 5 times 2, we get 4. 5 times 3, we get 3. 5 times 4, we get 2. Now it's interesting, so 5 times 5 equals 1 mod 6. So in our case, private key and public key would be the same. So what I can do is, remember, we have an equivalence principle. I can also do 5 times 11 equals 1 mod 6. Why? Well, 5 times 11 is 55. 55 divided by 6 equals 9. There's 1 rest over. And that's that. And this is how I get my private key. And this is how all the magic is happening in RSA. It's 5 super simple steps. Pick P and Q, large prime numbers, they stay private. Multiply them together, this is N, this is public. You can give this out because you cannot go from N back to P and Q if they are large enough. Calculate Euler's phi, which are the amount of numbers that are co-prime to n in between. This stays private. Pick one of the numbers. Normally, they're very small. You give them to the public. You calculate and make sure they're co-prime using the basic Euclidean algorithm. We're not going to go into depth, exactly like we're not going into Euler's theorem, into showing that the phi number is actually the numbers that are co-prime. Then calculate the inverse to your public key, and that becomes the private key. You do this with the extended Euclidean algorithm, and that becomes the private key. And that's how we have the 5, which is the public key. 11, we could also pick if you wanted to. We could add another 6, so we could use 17. Would work as well. And this is how the entire magic of RSA is happening. But so now, obviously, this is the interesting part. So, quick summary. If you wanted to do signing, instead of doing message to the power of 5, we would use message to the private key first, which is 11, and then the other person could verify this with their public key. But so now the more interesting question on this entire 5-step thing is, why the heck does this work? Basically, what you are asking, and this is the key thing, is m, message, to the power of first the decryption key, then the encryption key, equals the message again mod n. This is what you're asking. Because how is it possible that I have m, I do a mod, I get a number, I do another power with the encryption with the decryption key. So first it's sorry, I have the e and n wrong always. So that's encryption first, then decryption. And how come I get the message out again? And so here is where it's important to understand this third step. This is where the key thing is happening here. Because obviously this phi is so powerful. And this is now where it gets very important. So remember, maybe from the last episode, if you remember this, we had this part where if you went far enough in a group or in a field, in a finite field, for example, suddenly you ended up at the same place again. Or if you have a clock, there is this number of steps you have to take that you end up at the same number. And it doesn't matter if this is a 0 or you call this a message. And so the only question is, how often do you have to go around in a circle to end back up again? And there's something, again, we're not going to go into it, Fermat's little theorem that proves a couple of things. And it's just important you understand this. So many YouTube videos go into great detail. If you're interested in this, go through it, but it's way more important to understand why this actually works. And what this thing actually says is, and you have seen this actually, you can watch the videos from before. If you raise a to a prime number minus 1, so you don't go the full prime, you end up at 1 mod this prime number. And you can see this in the example where we had mod 11 in the last example. We always ended up at 1 if we only went 10 steps. So now it gets interesting. If we go a to the power of p, we actually end up at the message at a mod p. So if you want to try this, we can go and do 2 to the power of 6 equals mod 7. So it's 7 minus 1. And you can try this out. It gets to 1. And if we 2 to the power of 7 equals what? 2 mod 7. If you want, calculate this through. And you will always see this. Now here now is what's called the Carmichael function. The Carmichael function actually uses the absolute 1 round. So what does it take to just go 1 round around so that you end from here to here? How often do you have to raise it based on this number to just go 1 round? And Euler's phi is just way easier because what actually Euler's phi says, and this is very interesting, if you raise, and let's use n in this case, right? Let's say you raise a message to Euler's phi plus 1, you get the message mod n. This is really important. That's why we need this phi function, because we get there. And now you also understand why we need to do step 4 and step 5. Because if you think about it, 1 mod phi, which is exactly what we're doing here in step 4, from step 4 to step 5, we're doing nothing else than calculating the inverse. So we are picking a number, and then we ask, so we have a number here, which is the encryption key, and we ask this times what equals 1 mod phi. But 1 mod phi is nothing else than phi plus 1. And this is now where the trick is happening. The trick is that we can get E times D in there. And it doesn't matter which way we go first. Do we go D first or E first? We might go several rounds until we land at the message again. And you can try this out if you want. This is the power of RSA. The power is to understand a few of these very basic mathematical principles, and they have been known for hundreds of years. They're very, very basic. What Rivest, Shamii, and Adelman just understood is, and this is really the key thing, if I pick 2 prime numbers, P and Q, make them really, really large, pick an N, I can calculate this very easy. I can make this N public, but no one knows P and Q. It's very, very difficult to do prime factorization. What I can do very easy is I can calculate phi, because this phi is just P minus 1 times Q minus 1, and that is if I do mod n to go for a full circle. So all I do now is I split up this phi. I split it in a public key, and I calculate the private key. And that allows me to go into in a full circle in the modulus function and always end up at the same message. And that is what is such a genius. And this is why RSA to me is always so fascinating, because what these guys understood is the power of very, very basic math that is very difficult to calculate if you actually think about it. And that is, in my opinion, why it is really relevant to understand this. Not understand to calculate every single piece of math. We have enough math in there. And again, you can look up the Carmichael function, you can look up Fermat's little theorem, you can look up the extended Euclidean algo, you can look up the basic Euclidean algo, you can look up Euler's theorem, how Euler's phi, or also called the Euler-Stoichern function works. You can look all this up. It's not that relevant. You need to understand the basics. And these are the basics. And this leads us to the final last question. If we talk about cryptanalysis, then how easy is it to hack RSA? And so there's a couple of things. The first, and that's the most important thing, if you make n public, which you can, right? Or you have to, because that's what everyone has to know. N has to be public. Uber large number. Phi has to be private. That is something that's very, 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 very important. If you know phi, you know how many steps you need to go in this n in order to always lead to the same message. Then you just have to split phi, and you do this with the extended Euclidean algorithm, and then you can easily hack this entire thing. The other thing is, in order not to be able to calculate phi, that's important, P and Q have to be private. Very important, otherwise you can calculate phi. There's another thing that's very important. N not allowed to be a prime. Because if n was a prime, very important, that's why you need to have 2 primes multiplied. If n was a prime, well, I can just calculate phi very easily. Anyone can do it, because it's just -1, right? Very, very important to understand. Now, obviously, the other thing is length. Remember, P and Q at least 512 bits. And the last thing, and that's going to be interesting, because of Shor's algorithm, we're going to have a separate episode of this, right? Because of Shor's algorithm that works really, really well on quantum computers, over time, right? And the estimations are 2030 at the moment, so we still have like 15 or let's say 10 to 15 years, so we still have time to adjust. But probably at some point, RSA is going to be susceptible to quantum computers. And so that's going to be very interesting to see. We're going to have a separate episode a bit later when we go into this and we kind of look at this. But I hope this kind of makes sense to you. Let me know if you have questions. Let me know if you like this. Let me know if a light bulb went on and it got you this as excited as I got when I understood RSA for the very first time a long time ago. But I'm still excited because I always think how elegant this entire thing is. Let me know in the comments below. Give me a thumbs up if you want to be notified about the next videos on cryptography, on cryptocurrencies, blockchain, entrepreneurship, mindset. Click the subscribe button, click the bell button. Very important. And I'll see you soon at the next episode where we're going to be talking about the next asymmetric cryptographic method, which is Diffie-Hellman. So I hope I see you there. Yours truly, Julian.